Good morning, everyone. My name is Zhiying from Michigan State University. Today, I'm going to present this paper called MobiChem, a ubiquitous smartphone-based toolkit for practical fruit monitoring and analyze. This work is in collaboration with Abdul, Aziz, Patrick Du, and VP Nguyen from UMass Amherst, and also in collaboration with my advisor Tianxing from Michigan State University. In recent years, there has been a growing demand for high-quality fresh produce. So numerous economic surveys have shown that healthy food represents a global market valued at over $600 billion, and this figure continues to grow as the global standard of living rises. In particular, the market for fresh fruits is also projected to grow at an annual rate of 5.14% and above. However, there's a special thing about fruit as a food is that fruits can ripen very quickly. They undergo significant post-harvest physiological changes, and its nutrition values at different time of consumptions change also very quickly. So if this managed improperly, such variability in maturities can easily cause spoilage in transportation and storage, leading to considerable economic losses. In addition, for food consumption personally, underripe fruit can cause stomach discomfort or pose dietary risk for individuals or patients requiring those special or dietary controls. So this trend highlights a critical need for accurate and practical way to access fruit qualities. So for existing fruit sensing approaches, we can broadly categorize them into several types. The first includes those in-lab methods, such as HPLC chemical extraction, compression, profile analyze, or some puncture test. While this method are considered as accurate as the gold standard, they are destructive and lack portabilities, making them suitable only for laboratory uses. In comparison, there is a growing need in our community recently for more accessible sensing techniques. So we have seen approaches using terahertz sensing, Wi-Fi sensing, multispectral imaging. And this method are non-destructive and thus more practical for real-world applications. However, they still require dedicated hardware, which introduce limitations in terms of the mobility. So to enhance the mobility, the most intuitive approach is to leverage the rich array of sensors already available on modern smartphones. So consider everyday scenarios such as in grocery store. This offers the most portable and lightweight sensing solution. However, in current research on this landscape, there still remains a gap in achieving truly smartphone-based sensing approach. For example, we have invested a group of smartphone-based systems. They all use smartphone camera and apply some sort of spectral analyze to do the fruit quality sensing. To be honest, the best way to describe them is that they are all smartphone plus some additional active components method. So they still require additional external components such as external sensors, microcontrollers, or even the mechanical parts there. This undermines the purpose of using smartphone itself as a self-contained sensing device. So we ask the question, can we deliver those type of non-destructive fruit monitoring on a commercial off-the-shelf smartphone without any active components? So the idea of our answer is actually very simple. We want to make use of the co-location property of the camera and display on a typical smartphone to achieve multispectral image sensing. So to illustrate what I mean, here is a typical high-end spectral imaging system. It contains two main parts. First, it has a camera as an image sensor, and it includes a lighting system that enables multi-wavelength light modulations. You may notice the interesting parallel on the high level. It also happens on the smartphone. That is, every smartphone has a co-located camera and a very bright display. So the idea is that we use selfie camera as an image sensor, and we use the display as a light source. So by modulating the light outputs through the mobile application, we're able to reproduce multispectral raw image capture, and this can provide the richer features for further analysis. Though the idea is very simple, there are a few aspects we need to address. First, the illumination principles for the display is actually different. There are limited spectral resolutions on the smartphone. Smartphone displays are typically limited to the 3 wideband peaks in red, green, and blue regions. One might think that we can generate multiple colors. However, those colors are just combinations of these 3 principal components. And a true multispectral image requires more optically distinct monochromatic wavelengths. So consider these constraints, we need a new way to generate additional spectrum peaks. The other challenge comes to our application itself, that we are training actually with a new device under limited data. So on the one hand, we use a new system to collect the samples, and such collection process has very light overhead, and there are limited similar public data set to borrow to learn. And for our own collected data, the natural fruits we collect for certain samples can be imbalanced and relatively small in terms of the numbers. So on the other hand, we aim to provide a diverse sensing for diverse fruit types and properties as much as possible. We hope the system can perform fruit analysis for any general fruit types with different number of maturities and different properties at varied unit scales. So with this dilemma, the challenge is to design a robust training framework to achieve the goal. Therefore, we propose our system. It mainly contains two parts. So in the hardware parts, we will solve the first question about new light spectral generation. And in the second part, on the software backend, we will solve the second question. We'll talk about the tricks of training robustly. So let's dive them one by one. So the first question we ask is, how do you generate more spectral light? I need to stress the requirement again that we don't want to use any active component. So our answer to this question is quite simple. In one phrase, optical filters. So an optical filter is a piece of glass or plastics that lets certain wavelengths of light pass through while blocking the others. How will this solve the problem? Let me explain in detail. So although phone screens only emit these three primary colors, red, green, and blue, by analyzing a dozen OLED panels, we can say that spectral peaks are fairly broad and exhibit noticeable overlap. That means there are useful light components in the sideband regions of each peak that we may be able to isolate and extract as an additional light source. So to do this, we can just purchase filters off the market. Nowadays, these things are actually very cheap. Each piece there is at most like $1, and there are very diverse options on the market you can choose. So these are just few examples of the filter transmission ratio there. In actuality, there are hundreds of them, but we narrowed down the selection process to two criteria. First, we need the after filter light intensity to be sufficient, so we set a minimal intensity cutoff. That is, efficient after filter light should retain a non-trivial amount of the phone peak intensity. Second, the filter light must have distinct wavelengths from the three red, green, blue we already have. So in practice, we set the peak deviation cutoff require at least a separation between the peak wavelengths to ensure resolution among the usable spectral band. So this selection process is automated, and for any smartphones, we just use the factory-provided data on the spectral response at its full brightness. Once we set the two parameters we mentioned previously, which is minimal intensity cutoff and peak wavelength spacing, the system can search through hundreds of filter candidates to identify the most suitable choice for any smartphone, and along with the corresponding backlight and control sequence. So at the same time, we also design a simple filter mounting system to ensure proper alignment to the display. So by inputting the phone's parameters, including this, we can generate a compact filter rack and portable enclosures as part of the toolkit. This geometry is then converted into a 3D printable parts for the and customizable manufacturing. So take the example of OnePlus Pro, this phone model. Here as you can see, this is the final 3D printed components. It includes a foldable case for easy portability and to accommodate fruit samples of various sizes and volumes. And the filter lid ensures precise placement of each filters. Just to highlight this concave embedding structures, is actually a pretty secure and precise way to hold the filters with different sizes. So once it's assembled, the structure serves as a compact filter cover for the phone screen. So for example, in the end, we select 5 optical filters and position them in this manner. And we also left one open slot to allow the phone's original 3 colors to pass through. And on the top right, you can see these are the real measurement of the normalized spectral response for each illumination, 8 in total for OnePlus 8 Pro, demonstrating the effectiveness of our filter selection. And with this setup, we can proudly say that we have achieved the multispectral illumination on a smartphone. So for our prototypes, the capturing action is done as follows. So a program controls the display backlight, turning it on and off sequentially to the target wavelength. And for each illumination, the camera capture one frame, representing the spectral at that particular wavelength. So combining this frame form a data cube, and we pass for the next step of fruit analyze. So at this step, the question in essence is that we ask, how can we train the model robustly under a relatively small data collection overhead? So let's look at the performance under a baseline. So if we train an encoder and decoder and pass a multispectral data cube into the encoder and use it in the latent space with a simple neural net and a regressor for maturity and property analyze respectively, the result in practice is not ideas, but we want to understand the reason why it's not ideas. So we look at the latent space. So let's take an example of the chemical level prediction task latent space. The color of the dot representing the concentration values. And you can see this point, in terms of the color, is orderless. And they are too closely together, indicating the current setup struggle to learn some generalization about the fruit properties. And a prior for fruit property and maturity concentration is that, maturity and chemical concentration is that we know naturally they change continuously and gradually over time. So we can clearly see this fails to capture the continuous nature of the sample. So if we can enforce continuity in the latent space, embedding this kind of gradual change into the learning process, we may be able to improve the generalization and overall performance. So how do you do that? To make sure the continuity is learned in the latent space, we add a module after the original encoder in training called contrastive ranking. It has a loss function called rank and contrast. Mathematically, it has been proven to guarantee a desired order of learned representation and significantly improve robustness, efficiency, and generalization on a small data set. So we expect the result of this embedding to be continuous. In this case, it ensures a sample with similar labels are close together and ordered. So to give an example of the, in addition, we augmented our data set of the image with some synthesized transformation, such as image rotation, jitter and noise, and cropping. This I just used to expand the data set for further contrasting each sample to better enhance our performance. So compared to the original, which are orderless and meaningless, this approach captures an intrinsic order of the data, reflecting a continuity in the chemical and the physical properties during the ripening. So in the latent space, each dot is color representing each color dot is representing the concentration from low to high, and you can clearly see there is a smooth color progression, showing the model has learned this kind of incremental trends. If we look at the table, the impact on the prediction performance is also very evident. So to evaluate our system, we collect data from 170 tomatoes, 98 bananas, 73 avocados, and we collect them across 3 different seasons. Multispectral imaging data was performed using a 1+8 prophone, and we use a canonical mononica to obtain the ground truth. So this process gives us a paired multispectral image cubes and the label data for model training and evaluation. So to demonstrate system effectiveness, in addition to the absolute performance I will talk about, we're also comparing the result between the MobiChem's 8-channel input with RGB's 3-channel input. So this helps us understand whether those additional light extracted from the sideband of the RGB really contribute new information to our training. So we conduct 3 types of classification tasks for fruit maturity. Each of one fruit is actually a multi-class classification on its own. For example, tomato has 6 different stages, banana 7, and avocado 4. And 4 other regression tasks for various chemical and physical properties. Those are the regression tasks. So for the maturity classification, the x-axis are the fruit types, and the y-axis represent the multi-class classification of each maturity in terms of the accuracy in percentage. So blue bars indicating the performance of MobiChem's input. On average, it achieves like about 93% accuracy and consistently outperforms the baseline that use only the standard 3-channel RGB input. So to dive deeper, if you just take the example of the 6-class classification of tomato, look at the confusion matrix on the right-hand side. You can see it has much better in telling the subtleties of those neighboring classes that are visually very similar. So for example, the small difference between these 2 adjacent maturity stages are visibly very subtle and hard to detect. However, MobiChem can provide additional spectral data in 8-dimensional ways. That's why we can pick up those subtleties and differentiate better than RGB image. And we have picked some other neighboring classes that can be confusing in the RGB space of banana and avocado. And this is also applies. MobiChem is very good at picking out those subtleties. And for fruit property prediction, the x-axis shows the 4 target properties: lycopene concentration, chlorophyll concentration, sugar concentration, firmness concentration. And the y-axis are the R-square scores, where 100% means perfect one-to-one mapping. Overall, MobiChem shows an average improvement of 12% in the R-square score across all properties. And if you plot this actual value against the predicted values, the blue dots are MobiChem's data, and the the gray ones that is more scattered away are the RGBs. And you can see this still applies. So last thing I want to highlight is that we mentioned the contrastive Rankine learning. And even in the contrastive learning for feature embedding, we observed that under the same number of training epoch, the 8-channel MobiChem inputs learns faster and more effectively. We want to say it actually can better capture and enforce the continuity in this particular application domain in the meaning of fruit quality and maturities. So I'm nearly finished. So in conclusion, we introduced a system called MobiChem. It achieves practical fruit sensing on commercial off-the-shelf smartphone without any active components. It features a low-cost, zero-power customized filter design, extending multispectral illuminations beyond RGB on the smartphone. And we introduced Rankine contrast trick for fruit sensing module to make our analyzer robust under this limited setup. And MobiChem can achieve high accuracy in the application domain that we choose. So thank you guys. For more details, please read our paper.
Okay, please.
Hello, I'm Ray Xiao from Zhejiang University. So it's a very interesting work that uses visible light to do fruit sensing with a customized filter array. And so my question is, I have 2 questions. The first one is that, how the impact of the ambient light on the detection accuracy? And another question is about the scalability, for example, on different smartphone models, and how can we generate to scale to different fruits?
So the first question is asking about the impact on ambient light, and the second question is asking about the general smartphone application, right?
Yeah.
Did I miss anything?
Yeah, sure.
Okay. For the first one, actually, we indeed test in the 3 different locations. I think laboratory, office, and kitchen. The result is actually pretty uniform. But I think partially probably is due to that we have a foldable case design. That is the purpose to block the ambient light. And for the generability across all smartphones, just as we mentioned, the pipeline for selecting filters and also to mount the system on the phone screen is applied to any smartphone. Because we just need smartphone with a display and a front-facing camera.
So we can directly use the trained model on different smartphones.
And that's why we designed the training model to be robust, even under a small how do you say the word? Small calibration. Because the training process requires very less data for the data collection overhead. Yeah.
Okay, thank you.
Thank you for the great talk. This is Shiming from Hong Kong PolyU. And I have a similar question as Ray, that about the implementation. That when we run an AI model on the smartphone, and can we use like a general or unified Android app, or we have to deploy the model on a specific phone, like the OnePlus smartphone you mentioned in your slides? Thank you.
The model is not phone specific. And I can tell you for the 3 fruits that we are experimenting on, they're all training on the same model structure. So there's no difference. So it's not like biased towards any type of fruit. But the fruit has to be in your training data. Otherwise, it's just guessing, right?
Yeah, thank you for the answer.
Hi,
Thank you for the presentation. I'm Jun Lee from Yonsei University. I'm curious about because you're using a spectrum of the screen, and I'm pretty concerned about the burnings of the screen, especially we're using an OLED, and sometimes we lose some kind of the brightness of some LEDs, especially the blue. In your experimentation, was there a kind of did it work okay when you lose some kind of a spectrums, or?
Sorry, I didn't hear. Lose what? Last word. The last word of your question. Losing. What?
Yeah. So was it okay for your models to work with loss of spectrums? What I mean is that this. I think that this your work is really important to gather all the spectrums of the the screen.
Yeah. So, okay, the first question you're asking on the power, the harmonies to the phone screen, right? Whether this kind of like light will harm the phone screen. It's actually a very good question. We didn't test that, but I'm happy to explore. And for your second question, I think it's probably come down to why we choose 8 channels. Why not 7 channels, 6 channels? So the short answer is that this is the sweet point we find that work the best, because it's a trade-off between the illumination intensity, because it takes the space of the display. But we haven't investigated what is really the optimized number, whether 8 channel works the best than the 9 channel, we don't know. But currently, with 8 channel, these are as good as the result we can get for now.
Thank you.
We're happy to do more. It's a continuous research,
Thank you.
So let's give a round of applause. Thank you again. For